Okay, well, welcome back to our class on algorithms and data structure. We are continuing along in our development here. We talked about inheritance and polymorphism, and then we talked about inheritance and list. And for this lecture, we're going to get into searching. So let's go ahead and go through that. So this is the various topics. And so just quickly from the textbook chapter contents, we'll talk about the common need for doing searching an unsorted array, searching a sorted array, searching an unsorted chain, and searching a sorted chain. And then finally, we'll talk about choosing a search method. So people are always looking for something, be it a date, a mate, or a lost sock. And so those may be some examples. In fact, searching is one of the most common tasks done for us by computers. Just think of how many times you search the internet. This chapter looks at two simple search strategies, the sequential search and the binary search. You can use these strategies when implementing the method contains for either the ADT list or the ADT sorted list. Binary search is usually much faster than a sequential search when the data is sorted and is an array rather than a chain of linked nodes. Sorted data, however, usually takes much more time than searching it. This fact should influence your choice of search method in a given situation. So it's not always the same answer for every problem. So in terms of the problem, so these are examples of everyday searches. Like the people shown in this figure, you can search your desk for a pen, your closet for a favorite sweater, or a list of names to see whether you were on it. Searching for a particular item called the target among a collection of many items is a common task. So let's talk about an iterative sequential search of an unsorted array. The implementation of contains, as given in segment 1113, uses a loop to search the array, ignoring its first element. Using logic like the method contains, the following static method searches an entire array of objects having the generic type T for a particular object and entry. So the loop exits as soon as it locates the first entry in the array that matches the desired item. In this case, found is true. On the other hand, if the loop examines all the entries in the array without finding one that matches an entry found, remains false. Figure 19.2 provides an example of these two outcomes. For simplicity, the illustrations use integers. So here is part A, and here is part B. So we begin a sequential search of an array by looking at the first entry in the array. If that entry is the desired one, we end search. Otherwise, we search the rest of the array. Since the new search is also sequential, and since the rest of the array is smaller than the original array, we have a recursive description of a solution to our problem. For the most part, we need a base case. An empty array could be the base case because it never contains a desired item. For the array A, we search the n elements A0 through AN-1 by beginning with the first element A0. If it is not the one we seek, we then search the rest of the array. That is, we search array elements A1 through AN-1. In general, we search the array elements A first through AN-1. To be even more general, we can search array elements A first through A last when first is less than or equal to last. So the pseudocode that we're showing here describes the logic of our recursive algorithm. The method that implements this algorithm will need parameters first and last to spare the client the detail of providing values for these parameters and to allow the method in array to have the same headers as it did in segment 19.3. We implement the algorithm algorithm as a private method search that InArray invokes. So we're showing that here. So in this figure, we're illustrating a recursive search of an array. And so you can look that over. And here is some more details of doing a sequential search. So what about the efficiency of a sequential search of an array? Whether you implement a sequential search iteratively or recursively, the number of comparisons will be the same. In the best case, you will locate the desired item first in the array. You will have made only one comparison, and so the search will be big O notation 1. In the worst case, you will search the entire array. Either you will find the desired item at the end of the array, or you will not find it at all. In either event, you will have made n comparisons for an array of n entries. The sequential search is the worst case, is therefore big O notation n. Typically, you will look at about 1/2 of the entries in the array. Thus, on average, the case would be big O n over 2, which is, so you can be thinking about that. So searching a sorted array, a sequence search of an unsorted array is rather easy to understand and to implement. When the array contains relatively few entries, a search is efficient, even enough to be practical. However, when the array contains many entries, a sequential search can be time consuming. For example, imagine that you are looking through a jar of coins for one minted during the year of your birth. Sequential search of 10 coins is not a problem. With 1,000 coins, a search could be lengthy. With 1 million coins, it is overwhelming. A faster search method would be welcome. Fortunately, faster search methods are possible. Well, let's talk about a sequential search of a sorted array. Suppose that before you begin searching your coins, someone arranged them in sorted order by their dates. If you search the sorted coins in figure 19.4 sequentially for the date 2000, you would look at the coins dated 1995, 97, 98 before arriving at 2000. If instead you look at the date 1999, you would look at the first 4 coins without finding it. Should you keep looking, if the coins are sorted into ascending order and you have reached the one dated 2000, you will not find 1999, but beyond it. If the coins were not sorted, you would have to examine all of them to see that 1999 was not present. What about a binary search of a sorted array? Think of a number between 1 and 1 million. When I guess at your number, tell me whether my guess is correct, too high or too low. At most, how many attempts will I need before I guess correctly? You should be able to answer this question by the time you reach the end of this section. So you can think about that as you're reading the text. If you have to find a new friend's telephone number in a printed directory, what would you do? You might open the book to a page near its middle, glance at the entries, and quickly see whether you were on the correct page. If you were not, you would decide whether you had to look at earlier pages, those in the left hand of the book, or later pages, those in the right half. What aspect of the telephone directory enables you to make these decisions? The alphabetical order of the names does. If you decide to look at the left half, you could ignore the entire right half. And in fact, you could tear it off, the right half off, and discard it. As in the figure, we're showing that you have reduced the size of the search problem dramatically as you have only half of the book left to search. You then would repeat this process on this half. Eventually, you would either find a telephone number or discover that it is not there. This approach, called a binary search, sounds recursive, and that would be a good observation. So let's adapt these ideas to searching an array of n names that are sorted into an ascending order. Note that descending order would also work with a simple change in the algorithm. So we know that A0 is less than A1, less than or equal to A2, all the way up to less than or equal to AN-1, because the array is sorted. We can rule out the whole section of the array that could not possibly contain the name we are looking for, just as you rule out an entire half of the telephone directory. For example, if you're looking for the name David, we know that A5 is equal to Jamie, then of course we know that Jamie is before A5. But we also know that David cannot appear after A5 in this array because the array is sorted. That is, David is less than A5 is less than or equal to A6, all the way is less than or equal to AN-1. We know that this without looking at the entries beyond A5. We therefore can ignore these entries as well as A5. Similarly, if the sought after name after A5, for example, if we were looking for Mia, we could ignore A5 and all the elements before it. Replacing the index 5 in the preceding example with whatever index is in the middle of the array leads to our first draft of the algorithm for a binary search of an array. And so that's what we're showing here. When complication arises, however, when we write the recursive call to a previous pseudocode, each call searches a sub-range of the array. In the first case, if the element indexed by 0 through mid -1, in the second case, the elements indexed by mid +1 through n-1. Thus, we need two extra parameters, first and last, to specify the first and last indices of the subarray of the array that is to be searched. That is, we search a first through a last for a desired item. Using these parameters and making the recursive calls looks more like Java, we can express the pseudocode as follows, and we're showing that here. Now that in each recursive call, either the value of first is increased or the value of last is decreased, if they ever pass each other and first actually becomes larger than the last, we have run out of array elements to check. In that case, desired item is not an array. If we add this test to our pseudocode and refine the logic a bit, we get the following more complicated and complete algorithm. So here in the figure, it provides an example of a binary search. And you can see how it's cutting it roughly in half, and you're slowly getting to where you want to go. This is just some more details here. So we'll just move on. So although the implementation of the sequential search that were given in segments 19.3 and 19.6 use the method equal to make the necessary comparisons, the binary search requires more than a test for equality. To make the necessary comparisons, we need the method compared to. Since all classes inherit equals from the class objects and can override it, all objects have the method equal. But for an object to have compared to, it must belong to the class that implements the interface comparable. Such is the case for objects in sorted list, as segment 17.1 of chapter 17 indicates, and for objects in a sorted array. The method binary search can have the following implementation. And so you can keep that in mind here as we're looking at the slide and the listing. So for the Java class library, the method binary search, the class arrays in the package Java util define several versions of the static method binary search with the following specification. And so you can see that. So what is the efficiency of the binary search of an array? The binary search algorithm eliminates about half of the array from considerations after examining only one of its elements. It then eliminates another quarter of the array and then another eighth and so on. Thus, most of the array is not searched at all, saving much time. Intuitively, the binary search algorithm is very fast, but how fast is it? Continuing the comparison that occurs will provide a measure of the algorithm's efficiency. To see the algorithm's worst case behavior, you count the maximum number of comparisons that can occur when searching an array of n elements. Comparisons are made each time the algorithm divides the array in half. After each division, half of the items are left to search. So let's talk about an iterative sequential search of an unsorted chain. So in figure 19.7, which we're showing, it illustrates a chain of linked nodes that contain the list entries. Recall from segment 12.8 of chapter 12 that first node is a data field of the class that implements the list. While it is clear that a method can access the first node in this chain by using the reference first node, how can it access the subsequent nodes? Since first node is a data field that always references the first node in the chain, we would not want our search to alter it or any other aspect of the list. Thus, an iterative method contains should use a local reference variable current node that initially contains the same reference as first node. To make current node reference the next node, we would execute the statement, and we'll be seeing this here in this slide. So the iterative sequence search has the following straightforward implementation. So this is the implementation of the iterative search and contains. The private recursive method search examines the list entry in the node that its parameter current node references. If the entry is not the desired one, the method recursively calls itself with an argument that references the next node in the chain. Thus, the method search has the following implementation. You can see that in the chart. So searching a sorted list, we now search a chain whose data is sorted. Such a chain would occur in a linked implementation of the ADT sorted list. For a sequential search of a sorted list, searching a chain of linked nodes whose data is sorted is similar to sequentially searching a sorted list as described in segment 19.8. Here we incorporate that logic into the following implementation of contains, and you can see that in the chart. Now for a binary search of a sorted chain, a binary search of an array looks first at the elements that is at or near the middle of the array. It is easy to get the index mid of this element by computing first plus parentheses last minus first divided by 2, where first and last are the indices of the first and last elements respectively in the array. Assessing the middle element is also easy for an array A. It is simply a mid. Now consider searching a chain of linked nodes such as the one you saw earlier in figure 19.7, whose nodes are sorted. How would you access the entry in the middle node? Since the chain has only 3 nodes, you can get to the middle node quickly. But if the chain contains 1,000 nodes, in general, you need to traverse the chain beginning at first node until you reach the middle node. How do you know when you get there? If you know the length of the chain, you can divide the length in half and count nodes as you traverse. The details are not important as a realization that it takes a bit of work to access the middle node. After looking at the entry in the middle node, you probably need to ignore half of the chain and search the other half. Do not change the chain when ignoring part of it. Remember that you want to search the chain, not destroy it. Once you know which half to search, you must find its middle node, again by traversing the chain. It should be clear to you that a chain search of a linked chain of nodes would be challenging to implement and less efficient than a sequential search. So let's just summarize here and think about choosing a search method. So you can be thinking between a sequential search and a binary search. So we saw that you should use a sequential search to search a chain of linked nodes. But if you want to search an array of objects, you need to know which algorithms are applicable. To use a sequential search, the objects must have a method equals that ascertains whether 2 distinct objects are equal in some sense. Since all objects inherit equals from the object class, you must ensure that the objects you search have overridden equals with an appropriate version. To provide a binary search on an array of objects, on the other hand, the objects must have a compare to method and the array must be sorted. If these conditions are not met, you must use a sequential search. If both search algorithms are applicable to your array, which search should you use? If the array is small, you can simply use a sequential search. If the array is large and already sorted, a binary search is typically much faster than a sequential search. But if the array is not sorted, should you sort it and then use a binary search? The answer depends on how often you plan to search the array. Sorting takes time, typically more time than a sequential search would. If you plan to search an unsorted array only a few times, sorting the array so that you can use a binary search likely will not save you time. Using a sequential search instead. So what we're showing in this chart, the figure 19.8, it summarizes the time efficiency of the sequential search and the binary search. Only the sequential search is applicable to unsorted data. The efficiency given for the binary search are for a sorted array. For a large sorted array, the binary search is typically much faster than a sequential search. So finishing up with choosing between an iterative search and a recursive search. Since the recursive sequential search is tail recursive, you can save some time and space by using the iterative version of the search. The binary search is fast, so using recursion will not require much additional space for the recursive call. Also, coding the binary search recursively is somewhat easier than coding it iteratively. To convince yourself of this, try to code an iterative version of the binary search. Okay, well, that's it for this lecture, and thank you very much.